Our first type of double displacement reaction is a precipitation reaction. The general form for this is AB plus CD yields AD plus CB. And generally what happens here is two solutions, aqueous solutions, where ionic compounds are dissolved in water are mixed together, and then a precipitate forms, which is a solid, and the other ions remain dissolved. So our first one is lead 2 nitrate aqueous added to sodium chloride aqueous forms lead 2 chloride solid, which is the precipitate, and sodium nitrate aqueous. The second reaction, we have calcium chloride aqueous being added to aqueous potassium sulfate. It forms solid calcium sulfate, that's the precipitate, and potassium chloride. Now at this point you want to go ahead and pause the podcast and balance these equations, and when you resume you can check to see how your answers look. Double displacement reactions, the general form here is compound AB plus compound CD will yield new compound AD plus new compound CB. Now A and C are metals generally, and B and D are nonmetals, usually anions, and the exception of this is when you have an acid, but generally A and C are metals. And in this first type that we're going to talk about, precipitation reactions, our first reaction is lead 2 nitrate aqueous being added to aqueous sodium chloride and forming lead 2 chloride and sodium nitrate aqueous. The lead 2 chloride, of course, being a solid. And you can see here that certainly the lead 2 chloride is the precipitate or the solid. In the next one, the calcium chloride plus the potassium sulfate yields a calcium sulfate precipitate, so that is a solid, and then the 2 potassium chloride. So as you balance those, it's 1, 1, 1, and 2 as you read left to right. Another type of double displacement reaction is a neutralization reaction. In this one, we add an aqueous acid to a metal hydroxide, which is a hydroxide base, and we form salt and water. Now, a salt is just an ionic compound. We like to think of salt as like table salt, but a salt really refers to any ionic compound. So the first one, we have HCl aqueous, which is hydrochloric acid, added to sodium hydroxide aqueous, and we form a salt, an ACl, which is one you're very familiar with, aqueous, and then water. And water here is a liquid form, so that's how that is. Our second reaction, we have H2SO4, which is sulfuric acid, added to potassium hydroxide, forming potassium sulfate and liquid water. And in our third reaction, we have phosphoric acid, H3PO4, plus potassium hydroxide, forming potassium phosphate as a salt and liquid water. And the reason these are neutralization reactions is that water forms and water is neutral. The hydroxide base, the OH, combines with the H from the acid to form water, and it neutralizes the solution. So that's what we're looking at there. Now, if you'll go ahead and pause the podcast and go ahead and balance these equations, and we'll take a look at the answers here momentarily. Welcome back. Let's see how you did in terms of balancing the equations. And again, you want to practice balancing equations as much as possible. It just takes practice. It's experience that makes you good at it. So we're going to try and give you as many experiences as we can with it. When you look at the first reaction, the HCl plus NaOH yielding NaCl and H2O, it's balanced as written. All the coefficients there would be 1. But remember, we do not write 1 coefficients. They're implied if no other number is there. For the second one, we have H2SO4 plus 2KOH is going to yield K2SO4 plus 2H2O. And then finally for the third one, we have H3PO4 plus 3KOH will yield K3PO4 and 3H2O. The next type of reaction we're going to talk about are synthesis reactions. And to synthesize something means to make something new. And essentially the general form for this is A plus B yields AB. Now, when we dealt with single displacement reactions, one of the things we talked about is that all single displacement reactions are oxidation reduction reactions. Um, Double displacement reactions are not. Double displacement reactions generally are not oxidation reduction reactions. The oxidation states of the atoms involved do not change. In synthesis reactions, most are oxidation reduction reactions. Any synthesis reaction that involves elements on your reactant side going to a compound in products is always a oxidation reduction reaction. But there are some synthesis reactions that involve two compounds combining, forming one new compound, and those may or may not be. So let's take a look at the general form again. A plus B yields AB. When you see multiple reactants in a single product, you should be thinking synthesis reaction. So here we have the formation of solid sodium chloride from sodium and chlorine. We have the formation of aqueous magnesium hydroxide by adding solid magnesium oxide to water. We have the formation of liquid water from a combination of hydrogen and oxygen gases. And finally, the formation of aqueous carbonic acid, H2CO3, by putting carbon dioxide gas into water. And this happens all the time at companies that make your carbonated beverages like Pepsi, Coca-Cola, that type of thing. So if you will go ahead and balance these equations, pause the podcast and come back, we'll take a look at the answers. So let's take a look at these equations. Balanced 2Na plus Cl2 yields 2NaCl. The MgO plus H2O yielding MgOH2 is already balanced. 2H2 plus O2 yields 2H2O. And finally, CO2 plus H2O yielding H2CO3 also is balanced as written. Next, we have decomposition reactions. The general form for this is AB, which is a compound, will yield A plus B. This can be either a compound on the left forming, if it's a binary compound, forming two elements on the product side, or sometimes you'll have a compound on the reactant side that when it decomposes actually forms two compounds on the product side. Now, when a binary compound decomposes to its constituent elements, that always is an oxidation reduction reaction. When a compound decomposes to two other compounds, it often is not an oxidation reduction reaction. So you just have to look at the individual reaction to tell. But again, that's something we'll get into later on. Let's look at 4 examples here. The first, we have mercury 2 chloride decomposing to mercury and chlorine. The second, we have potassium chlorate decomposing to potassium chloride and oxygen gas. In the third, we have a metal carbonate, sodium carbonate, decomposing to sodium oxide and carbon dioxide. And in the fourth, we have a metal hydroxide, sodium hydroxide, decomposing to sodium oxide and liquid water. So if you will go ahead and balance those reactions and pause the podcast, and when you're done balancing, we'll come back and take a look. So welcome back, and let's see how you did with the balancing. The first reaction, the decomposition of mercury 2 chloride, is balanced as written. The second reaction, the balancing goes like this. 2 potassium chlorates will yield 2 potassium chlorides and 3 O2s. The third one, the Na2CO3 decomposes to Na2O and CO2. That is balanced as written. And then finally, the 2NaOH yielding Na2O plus H2O is balanced with the 2 in front of the NaOH, and you're done there. Now, these decomposition reactions, when we get to the podcast where we'll talk about predicting what chemical reactions will be, we'll talk more about what to do with chlorates, carbonates, and hydroxides as they decompose, what their products will be. The last type of reaction we want to deal with is or are combustion reactions. The general form of these is there will be a hydrocarbon, and a hydrocarbon is just some combination of carbon and hydrogen. Now, sometimes in combustion reactions, you'll see carbon, hydrogen, and oxygen, or some other third or fourth element available. We're going to deal right now with just compounds that contain carbon and hydrogen. These combine with oxygen to form carbon dioxide and water. So general form C sub M, M just representing a certain number of carbons, with H sub N, which represents a certain number of hydrogens, plus O2 yields CO2 plus H2O. Now here are 4 reactions, C3H8 plus O2 yielding CO2 and H2O. C3H8 is propane, which if you live out in the country and have gas heat, the likelihood is that it is propane heat. The second is C2H6, which is known as ethane plus oxygen, again forming carbon dioxide and water. The third one you've seen before, C8H18, which is octane, which is a major component in gasoline, plus oxygen forming carbon dioxide and water. And then finally, we have C4H10, which is known as butane, and the common BIC type lighters that you see have butane in them, plus oxygen forming carbon dioxide and water. Okay, so if you'll go ahead and balance those and pause the podcast, and when you're done balancing, come back and we'll see how you did. Well, let's see how you did. Here's a general hint for balancing hydrocarbons, and this works when you have just carbon and hydrogen bonded together. And here's what I do, is I take the number of hydrogens in the hydrocarbon and I divide it in half. If the number of hydrogens divides in half to an odd number, not an even number, but an odd number, I'll immediately put a 2 in front of the hydrocarbon before I begin to balance. When I do this, it will ensure me is that there will be an even number of oxygens on both sides of the equation to balance, so I don't have to worry about ending up with a fractional coefficient that I then have to mess with. It's just an easier way of starting to balance. So when I look at C3H8, 8 hydrogens divides in half to 4, so I don't double that, but I do get 3 CO2, 4 H2O, and 5 O2 to balance that equation. My C2H6 does divide in half. 6 divides in half to 3, so I immediately put a 2 in front of the C2H6. That yields 4 CO2 and 6 H2O. I balance my oxygen last, and 8 plus 6 is 14, so there are 7 oxygen O2s that I need to balance the 14 oxygens on the right-hand side. The C8H18 should have been pretty easy for you because we did this together earlier. Go ahead, because the 18 divides in half to 9, put a 2 immediately in front of the C8H18, gives us 16 CO2s, 18 H2Os. That gives us 50 oxygens on the product side, so we have to balance the reactant oxygens by putting a 25 coefficient in front of the O2. And then finally, C4H10, the 10 hydrogens divide in half by 5, so put a 2 immediately in front of it, and then we get 8 CO2s, 10 H2Os, 16 and 10 is 26 oxygens on the product side, so we have to have 13 O2s in order to balance that. Well, time for the infamous your turn problems here. Now, the next slide is going to contain reaction equations. What I'd like you to do is balance the equations and classify them using the following system. If it's a synthesis reaction, just put an S. Decomposition, put a D. Single displacement, put an SD. Double displacement, put a DD. And for combustion, put a C. So when you get to the next slide, go ahead and pause the podcast, write the equations down, and go ahead and do them, and then resume the podcast when you're ready. And here are the reactions for you to go ahead and do. So write them down, pause the podcast, and resume when you're ready. Okay, welcome back. Let's take a look at the first reaction, A. Here we have sodium oxide decomposing to sodium, metal, and oxygen gas. This is a decomposition reaction. We have a single reactant, which is a compound decomposing or separating into its constituent elements. This is also an oxidation reduction reaction. In order to balance this, we have to have 2 Na2Os yielding 4 Na and 1 O2. Our second reaction, we have a mixture of aqueous iron 3 chloride and potassium hydroxide solutions yielding an iron 3 hydroxide precipitate and potassium chloride, aqueous potassium chloride. This is a precipitation reaction, and it's a double displacement reaction. Here you have two compounds, and essentially what happens is the metals are switching places. So the iron is going with the hydroxide ion, and the potassium is going with the chloride ion. So in order to balance this, you need 3 potassium hydroxides and 3 potassium chlorides. Our third reaction is the C5H12. When we balance this, it needs 8 oxygens to form 5 carbon dioxides and 6 waters. Now, we did not have to double this because the hydrogens in the C5H12 divide in half to an even number, which ensures that we'll have an even number of oxygens on each side to compare. This is a combustion reaction, and hopefully you did well with that. Our fourth one, here we have calcium oxide reacting with liquid water to form calcium hydroxide. This is a synthesis reaction. You have multiple reactants in a single product, so this falls into the synthesis category. It is not an oxidation reduction reaction. None of these atoms change oxidation state, and in order to balance it, it's balanced as written, so that one is ready to go. Now for E, we have single displacement reaction where a halogen, chlorine, is displacing the iodide ion in solution. So we have Cl2 plus 2 NaI yields 2 NaCl plus I2. This is a single displacement reaction, and again, all single displacement reactions are also oxidation reduction reactions. Our reaction for F is hydrobromic acid added to sodium hydroxide, yielding sodium bromide, which is a salt, and water, which is a liquid. This is a double displacement reaction, and it is balanced as written. All the coefficients here would be 1. And finally, our last one, we have a single displacement reaction with an active metal, magnesium, displacing a less active metal, iron, in solution. So we have 3Mg plus 2 FeCl3, which is iron 3 chloride, yields 3 MgCl2 and 2 Fe. That is a single displacement reaction, and again, also an oxidation reduction reaction. How'd you do? Well, we have come to the end of our time here. I hope you did well with this. If you need to go back and review, please feel free to do that. Also, past podcasts that might be helpful to you is the one that is naming inorganic compounds. That could be very helpful to you. And there will be a future podcast on predicting chemical reactions that this will lead into as well. So my hope is that this goes well for you. If you need help, see somebody in your class who's doing well with this. They can help you. See your instructor. He'd be glad, or she would be glad to help you. And I wish you well with this.